Page 5 of the Stat Test 3 review from 2017. So we're looking at two population proportions. In this case, the study was conducted to determine if the ratio of passing touchdowns to passes attempted by Eli Manning had, right, so typo for somebody. Yeah, it wasn't always a typo when I created this problem back in either 2006 or 2007. It was fresh and new and current. But now, years later, it is a typo. In 2006, Manning attempted 522 passes, 24 of which were touchdowns. All right, so let's get that information down on the paper. So 522, 24 of which were touchdowns. I don't see any mentioning of means and standard deviations. So, you know, aside from it saying the title of two population proportions, we know that this has to be specific to that type of hypothesis test, because they also tell us information about 2007. So here's 2006. 2007 tells us that he had a few more attempts, 529, and actually less successes, less touchdowns. Oops, I guess I could tuck the two in there. Using a 0.05 significance level, test the claim that the population proportion of touchdown passes is significantly decreased between those years. All right, so if it's decreased, that means we started off with a number that was bigger previously. All right, so this is my first group, and this is my second group. So the claim here is that the proportion from group 1 is going to be, well, the null is always that there's equality. The alternative is related to the problem. The proportion for group 1 is more than the proportion from group 2. That shows a decrease. This problem may seem very familiar because we did one that was similar. We just used Peyton Manning's information rather than Eli Manning's information. And in a few years, we could use Arch Manning's information and Charlie Manning's information. You know, like we'll see if I can get this going down through the generations. Actually, maybe I'll even go back in time and get Archie Manning's information. You know, so a little first family of football action going on here. All right, so I'll make that the Easter egg for this video. If you can, and this should actually be for anyone, even if you're not a sports fan, because Peyton Manning and Eli Manning were brothers who played in the NFL simultaneously. All right, they're not currently playing together because neither of them are playing anymore, but they did at one point play in the NFL together. So what I would like, and this is open to anyone, for a bonus point, send me the names of two other siblings in any sport who played together at the same time. Okay, and so that'll be the Easter egg. And so it could be basketball, it could be hockey, it could be anything. All right, and so and then, you know, in the future, I'll see about making word problems related to those characters. So characters was a weird choice of words there, but it fits, I guess. So anyway, stat test. We're looking for the 2 prob Z test. And you can see the information that we have is tailor-made. 24, 522, 23, 529. Greater than symbol. Quackily. And so we're going to grab the p-value here. We know the alpha value, and I'll just jot down the alpha value. 0.05. The p-value is 0.04. Oh, that's, I'm looking at the wrong thing. 0.422. All right. So that is a massive p-value. All right, so the p-value, well, we don't really care how big it is. We just care about how big it is compared to the alpha value. So the p-value is greater than the alpha, so do not reject HO. All right. So what this is telling us is that there's no significant difference between the performances in the 2 years. And, you know, like you kind of look at it and say one of two things. I think anyway. One possibility would be, duh, look at the numbers. 24 out of 522, 23 out of 529. They're in the same neighborhood. The other possibility is you're like, okay, I don't know what any of this stuff means anyway, so who cares, right? But if you really kind of try to get at the idea that a hypothesis test is trying to essentially generalize something that you have observed. So you see information related to 2006 and 2007. So you look at it at first glance, you say, I wonder, that looks like it's a significant relationship. It looks like there's meaning to that. Like, if you put normal human being words to it, you might say, man, Eli got worse over the span of those 2 years, 2006 to 2007. And somebody else might look at it and say, well, I don't know what you're talking about. It looks like the numbers are around the same. This hypothesis test, this type of test, will verify who's right. Okay? And so I kind of look at it, and I tend to go off on a sports tangent every once and again, and I apologize for that if you're not interested. But what happened in previous year, I would say probably like the last 5 years, and this is related to Eli Manning, and it really kind of got me aggravated, is that the narrative in the media became Eli has lost it. He's not performing the way he used to. All right. So take that and you're like, okay, I don't know who Eli Manning is, but I do know who this politician is. I know who this actor is. You know, Tom Cruise isn't drawing in the box office the way he used to. You know, somebody makes that comment and people just go with it. This type of hypothesis test will actually determine whether there's statistical significance behind that. All right. So is there enough evidence to say that that's really a true statement? All right. That's the power of this type of test. All right. So, you know, I figured that was worth a couple of minutes of video time just because I feel like people just look at this and say, all right, yeah, I got an answer and that means something, I'm sure. I'm hoping that even if you don't fully get the notation and stuff like that, you get the underlying theory behind why it's important. All right. So there is, as we go right back to the templated conclusion writing, there is insufficient evidence to reject the claim that there is no difference in population proportion touchdown passes between 2006 and 2007 at the 0.05 significance level. Therefore, the claim of a decrease is false. I don't even know why I'm trying to write in script. That ship sailed a long time ago and then hit an iceberg and went under. What was the diamond called? That's the Easter egg. Oh, I actually know what it is. but I'll let somebody submit it. All right. So in the movie Titanic, what was the name of the diamond? All right. So the next page, a statistics professor has just gotten given a final exam and the results are listed below. Test the claim at the 5% significance level. The class performed on average better than the C+. So we need to make an assumption here. Assume C+ equals 75. On a test, I would give you that relationship. All right, because I know at some schools, well, C+ is typically 75. If it's a question of like GPA or something like that, sometimes it's a 2.3, sometimes it's a 2.5, so we got to be careful about things that are unreasonable assumptions. I think this is a reasonable assumption. All right, so HO would be that the mean performance is 75. The alternative is that it is more than 75. Just remember, generally what you're going to get, and this is 99% of the time, you're going to get the alternative hypothesis from the problem. Writing the null hypothesis is a simple matter of taking your alternative hypothesis and replacing the symbol that you have there, greater than, less than, or not equal, with just an equal sign. All right, that's all there is to it. All right, t-test, 5% level. This is raw data, so it's one of those things. You just got to look at it and say, I guess we're typing stuff in. That's part of the fun, I guess. All right, this is one raw list of data. And very easy to mess up. Feel free to advance this video by about a minute, because all I'm doing is typing in information here. No Easter eggs in this period of time. We're in the double checking phase. Okay. All right, so we're back. So my data's in. I'm going to quit out of here so that I don't accidentally type information into the stat editor. Stat, test, t-test. We had raw data. The benchmark is 75. My information was stored into L1. Each value I typed in a single time, and I want it to be a greater than symbol. All right. So, not too bad. Calculate. Just was doing a quick mental double check. So the p-value is equal to 0.0924. The p-value is greater than alpha, therefore do not reject the null hypothesis. All right. So there is insufficient evidence to reject the claim that the mean population mean, we already know what the sample mean score is, mean score is, now since we assume C plus is 75, we could say C plus or 75 at this point. I'm going to write 75 at the 0.05 level, significance level. Therefore, the claim that it is more than a C plus, because I want to get their terminology in there as well, more than a C plus is, well, not enough evidence to reject the null, which means that null is true, which means the alternative is false. And so there we are. So whatever the class average was here, it wasn't better than a C plus. All right, and so, you know, from an instructional perspective, that, I don't know, it all depends. You know, was it statistically better than a C? Was it better than a B? I mean, I shoot for a B. I shoot for a class average of B. We've talked about this back in the central limit theorem and normal distribution part of the course. You know, if you have a mean of 80 and a standard deviation of 10, that makes it unusual to get below a 60 and unusual to get above a 100, which I think is nice. It should be unusual, you know. So how many people failed the class, failed the test, the class, whatever, and you give the number, but that's unusual statistically. Okay, I mean, we can live with that. I got a 110 on the test. That sounds great. But then when you find out that everybody else got a 105, you're like, oh, it's great, but it's like just a little bit great, you know? So if you find out that you got 110 and that's unusual because the class average was 80, now you're walking in the clouds, you know, you're some awesome analogy that I can't think of. Anyway, so that's that particular hypothesis test. I think I'm going to squeeze one more into this video, and that is the independent samples, because it's along the same lines as the two population proportion, which we tackled with the Eli Manning question. All right, so it's got a little bit of familiarity. We have 16 randomly selected times at Burger Queen. So n is equal to 16. The average period, waiting period, x bar, 4.8 minutes. Let me just get my writing thing. My pen's starting to die, so here we are. With a standard deviation of 2. And then we go to Mickey G's. 14 times with a mean of 5.2 and a standard deviation of 1.8. The writing here is just like bothering me, so I need to make it look a little bit more legible. All right, so this all came from the first set of information, and this came from the second. So we have all the information that they were willing to give us. We know that alpha is going to be 0.05. Let's get our HO and HA. Can we say that there's a significant difference? Difference means not equal. So the mean, population mean waiting time, difference would be mu1 unequal to mu2. So that's my HA. My HO that corresponds to that would be that mu1 is equal to mu2. All right. So we have what we need. Stat, test, we're looking for the two sample t-test. So that's option 4. We're not working with data right now. We're working with summary statistics. So I'm going to hit stats, right arrow to stats. I'm going to type in the 4.8, assuming that it wants to let me go through this just about every time. 2 and 16, 5.2, 1.8, and 14. A not equal symbol. We keep the pooled setting to no because we can't guarantee that these waiting times are coming from distributions that have roughly the same standard deviation. Right? Now, if we were ever going to make the assumption, it would be for a problem like this, but we don't want to take the chance that we're going to say no. Right? And the reason why we could probably make the assumption here would be because if you look at the S values for BQ and McGregor's, they're about the same. And also, they're part of the fast food industry. Now, the assumption here is that we got to assume that these names are chosen to represent Burger King and McDonald's, so as in such a way so that I don't get sued. But without that being the assumption, we don't even know that they serve the same, populations. All right, one of them could be like a 5 napkins type burger, and the other could be like White Castle. I like White Castle. I don't like it the next day, but I like it. All right. So anyway, we're going to calculate the p-value about 0.569. All right. So very, very large. All right. So the p-value is greater than alpha. Therefore, do not reject the null hypothesis. All right, so there is insufficient evidence to reject the claim of no difference in population mean waiting times between Burger Queen and good old Mickey G's at I think the slogan for Mickey G's is I'm liking it, something like that. At the 0.05, I'm digging it, significance level. Therefore, the claim of a significant difference, which seems redundant, insufficient evidence to reject the claim of no significant difference, so we're keeping that one, which means significant difference has to be false. All right. So insufficient evidence to reject the claim of no difference in population mean waiting